Wastewater treatment. It's vital in protecting the environment and ensuring our health and safety as well. Untreated wastewater can contain harmful substances, bacteria, viruses, pollutants, and excess nutrients, which all pose a major risk to the environment and indeed humans if they were to be released untreated. In Australia, there are strict guidelines surrounding this process. However, in less developed countries, wastewater may be released directly to the environment. This can also occur in poorly maintained treatment plants or as the result of excess inflows. This has the potential to cause endless environmental issues and can affect the quality of life of affected communities. So, we know wastewater treatment is important, but what is wastewater? Most of us flush the toilet, drain the sink, shower, and wash our clothes without ever thinking of what happens to that water. In fact, any water that is used within the home that goes down a drain is defined as wastewater. So, where does this water go? Well, it ends up in a network of collection pipes known as sewerage, which in turn is pumped or gravity fed into a wastewater treatment plant. This video will reflect on a recent trip to one of Brisbane's wastewater treatment plants in the Redlands and outline the process stream that leads to treated wastewater being released to the environment. The first step in the process train of wastewater treatment is the inlet works. The inlet works is the first step within the wastewater treatment process. The inlet works is, as the name suggests, the inlet that feeds the treatment plant. Here, the raw sewage is pre-screened for solids and materials that cannot be processed or that may potentially block processes or pumps further along the chain. Unfortunately, as informed by one of the technicians, much of this screened material, referred to as RAG, is material that is not designed to be flushed into sewer systems, and a large proportion of this waste happens to be sanitary products. This pre-screened waste can amass to around 400 to 500 kilograms per day. This is unfortunate, as material that is not designed to be flushed or washed down a drain can block sewers and pumps and can increase maintenance costs. This speaks for the need for education on what happens to the water and the products such as baby wipes and other non-degradables carried with it after it has been used. Also contained within the inlet works is grit screening and collection. This consists of small particles that have not been digested along with other pieces of small material. Grit screening is an important process as the grit may pass through the process whole and contribute undesirable components to sludge and the dewatering process. These first processes are known as preliminary or primary treatment. The next step in the water treatment process is biological treatment. The next step after the inlet works is the biological treatment of wastewater by bacteria. There are many system designs for achieving this. However, most consist of a large tank separated by walls and baffles with specific aeration zones and directional flow. Using controlled anaerobic, aerobic, and anoxic conditions to facilitate the growth of bacteria for the removal of pollutants and nutrients is an efficient and cost-effective process and has been used in wastewater treatment for over 100 years. From the inlet works, the screened sewage enters the first section of the biological treatment process. This is the plant's anaerobic zone with a capacity of 1.1 megaliters. Anaerobic conditions in this tank favour the growth of anaerobic bacteria, which complete their role without the presence of oxygen. Anaerobic bacteria are used to reduce the volume of sludge to be disposed of and obtain the oxygen they need from the food they digest. From here, the wastewater enters the main section of the biological treatment tank with a volume of 9.9 megaliters. The brownish solution filling this tank is called activated sludge and is a flocculent culture of bacteria developed in this tank under very specific conditions. This tank possesses aerators and an oxidation ditch for the growth of aerobic bacteria. Aerobic bacteria need free dissolved oxygen present in the water to grow effectively, and the amount of dissolved oxygen is closely monitored and controlled. This tank also possesses anoxic or low to no oxygen conditions for an important process carried out by the activated sludge. The main goal of this biological treatment process is to remove nutrients, primarily high levels of nitrogen present as ammonia. Ammonia has the potential to be a toxic environmental pollutant in waterways, and excess nitrogen can cause algal blooms, fish kills, and generally decrease the quality of natural systems. Nitrifying bacteria grown in the aerobic zone are the first step in this process. Nitrifying bacteria consume ammonia present as NH3+ and NH4 along with the dissolved oxygen to produce hydrogen ions, water, and nitrite. The second part of nitrification involves differing bacteria, which consume nitrite produced in the first step along with oxygen to produce nitrate. Aerobic bacteria also require a source of non-organic carbon to feed on to effectively grow and are referred to as autotrophic. It is from here that heterotrophic bacteria, grown under the anoxic conditions present in the tank, can make use of the nitrate created by bacteria under the aerobic conditions. The process performed here is called denitrification and involves the conversion of nitrate to nitrogen gas, which is then released harmlessly to the atmosphere. Bacteria under anoxic conditions have a biological oxygen demand, or BOD, that they use as food and can use oxygen molecules attached to nitrate to produce nitrogen gas and hydroxide. For this process to work, there must be zero or very low levels of dissolved oxygen, otherwise the anoxic conditions required for denitrification will not exist and the bacteria will instead use dissolved oxygen. Nitrogen gas produced as a product of denitrification and heterotrophic bacteria can then be safely released to the atmosphere without worrying about pollution. As part of this process, a scum forms atop the activated sludge, which consists of filamentous waste. This is harvested at the treatment plant for disposal. At the end of this process, there exists a surplus of activated sludge that is no longer needed. This surplus activated sludge is then sent to a dewatering process via a waste activated sludge or WAS pump. Dewatering of the waste activated sludge is an important process as it allows this sludge to be properly processed and to further treat the water that is pressed from it. From the biological treatment process, as mentioned earlier, a WAS pump transfers waste sludge to the on-site dewatering plant. This plant uses a belt press, whereby this sludge is compressed between two belts and a series of rollers to extract water and create a solid. As the technician stated, this belt press produces a product that is around 14% solids, meaning much of the liquid still remains within it. However, even the most efficient dewatering systems may only achieve 20% solids. As can be seen here, the dewatering process separates water and sludge and transfers the sludge further into the plant for compressing. The filtrate from this process is returned back to the head of the plant for further treatment, whereas the solids are collected into large bins as can be seen in this video. This solid biowaste is removed from the site and sold to the agricultural sector for an effective fertilizer for animal feed crops. This dewatering plant has a capacity of 600 kilolitres per day and may produce 15 tonnes of biosolids every day. The next step in the water treatment process is clarification. Water leaving the biological treatment is pumped into two clarifiers, each holding 2.6 megalitres. The clarifiers are of a conical construction, allowing sludge and other particles to settle down towards the bottom of the cone and be collected and returned to the effluent intake of the biological process via return activated sludge or RAS pump. The water entering the clarifiers is pumped into a central ring, as can be seen in the center of the photo, and overflows into the main body of the clarifier. From there, the sediment begins to settle immediately as the water travels outwards. A weir that runs around the perimeter of the clarifiers ensures an adequate retention time to allow particles, sludge, and sediment to settle out. The water running over the weirs of the two tanks is clear, clarified water that is now ready for the final phase of treatment. This brings us to the final step within wastewater treatment, chlorination. The clarified water exiting the clarifiers is then transferred to the chlorine contact basin, which has a volume of 400 cubic meters in this particular plant. Chlorination is an important final step in the treatment process as it destroys or inactivates potential disease-causing pathogens that could impact human health if they were to be released to the environment. The chlorine contact time in this particular system is 1 hour, which is sufficient to decrease fecal coliforms and other potential pathogens to acceptable levels. However, before release to the environment, the water in the chlorine contact tank must be dechlorinated, as chlorinated water can negatively affect natural water systems. The addition of sodium bisulfate before environmental release almost completely removes residual chlorine. The water that is being released to the environment must follow guidelines for acceptable levels of key pollutants or nutrients and is governed by the plant's license. The result of this wastewater treatment process is a product that can be safely released to the environment and have no negative impacts on where it is released. For the Redlands treatment plant, this is the comparison table of license versus actual levels of key pollutants, nutrients, and other quality indicators. As can be seen, the actual levels fall well within the levels determined by their license and exceed expectations. In summary, the process train of this particular water treatment plant is the inlet works, the biological treatment, clarification, chlorination, and then release. This process outlined in this video is an efficient and cost-effective way to avoid the negative impacts of raw, untreated wastewater upon the natural environment.